Throughout the history of scientific exploration, humanity has continually sought to unravel the mysteries of our universe's origins. The most prevalent explanation for the universe's creation has been the Big Bang theory, which has held sway for much of the 20th and early 21st centuries. Thousands of scientists, across decades, have contributed to the refinement of this theory, offering a framework that fits much of the observational evidence we have about the cosmos. However, science is a dynamic field, one that continuously evolves with new discoveries and advancements in technology. And today, as cutting-edge instruments, such as the James Webb Space Telescope, JWST, bring unprecedented clarity and depth to our observations, the very foundations of cosmology, including the Big Bang theory, are being reconsidered. For over a century, the Big Bang theory provided the most comprehensive narrative about the universe's birth. According to this theory, around 13.8 billion years ago, all the matter, energy, and space we know emerged from a singular, incredibly hot and dense point. This point, often referred to as a singularity, was not just a point in space but contained all space itself. The universe then expanded rapidly in a phenomenon known as cosmic inflation, setting in motion the growth and evolution of the universe as we understand it today. Stars, galaxies, and eventually planets coalesced from the primordial soup of particles, driven by the forces of gravity and shaped by time. The idea that our vast, seemingly infinite universe could have arisen from such a minuscule origin was, and still is, awe-inspiring. Yet the more we peer into the cosmos, with the aid of advanced technology, the more questions arise about this theory. The recent observations, made by the JWST, which launched in December 2021, have brought some of these questions to the forefront. Its high-resolution images, capturing the universe as it was billions of years ago, are providing data that appear to challenge many of the expectations laid out by the Big Bang theory. Specifically, the telescope's discovery of over 750 galaxies that are older, smaller, smoother, and more numerous than predicted has caused ripples in the scientific community. At the heart of the controversy are these anomalous galaxies. According to the Big Bang theory, as the universe expands, objects further away should appear larger due to the relativistic effects of cosmic expansion. Yet the galaxies captured by the JWST defy this principle. They appear smaller, smoother, and older than expected. Rather than showing evidence of turbulent and chaotic formation processes, the galaxies are unexpectedly serene and organized, lacking the jagged and irregular structures that scientists believed would be typical of the early universe. Instead of finding evidence of young, immature galaxies, the JWST is showing us fully formed structures that, by all accounts, should not exist in such a nascent stage of the universe's history. These unexpected findings have led some scientists to reconsider what we know about the universe's formative stages. Traditionally, the Big Bang theory posited that during the early stages of the universe's expansion, matter was incredibly hot and dense, a period often referred to as the primordial fireball. From this state, space itself began to expand, carrying matter along with it. During this expansion, the universe cooled, allowing subatomic particles to form and interact. Over time, these particles coalesced into protons, neutrons, and electrons, which later formed atoms, primarily hydrogen and helium. This period is known as nucleosynthesis and marks the moment when the universe began to transition from a soup of particles into something resembling the matter we see today. Once the universe cooled further, these early atoms began to coalesce under the influence of gravity, forming the first stars and galaxies. The earliest galaxies, according to Big Bang cosmology, should be relatively small and disorganized, gradually merging and growing over time through cosmic collisions. Yet, the JWST's images reveal that some galaxies appear fully formed much earlier than the theory predicted. These galaxies do not show signs of having experienced numerous mergers, which challenges the notion that large galaxies evolve primarily through the collision and amalgamation of smaller ones. If these galaxies didn't grow through mergers, how did they form so quickly? And what does that mean for the broader story of the universe's evolution? The Big Bang theory, for all its successes, has long been supported by several key pieces of evidence. One of the most critical pieces is the observation of cosmic expansion, most famously noted by Edwin Hubble in 1929. Hubble discovered that galaxies appear to be moving away from us, with more distant galaxies receding faster than those closer to Earth, a phenomenon known as redshift. This observation gave rise to the idea that the universe is expanding, and by running that expansion backward, cosmologists concluded that the universe must have started from a single point. Another pillar of support for the Big Bang theory is the cosmic microwave background, CMB. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is faint radiation that pervades the entire universe and represents the afterglow of the Big Bang itself. It's a snapshot of the universe as it existed about 380,000 years after the initial event, when the universe had cooled enough for light to travel freely through space. The uniformity of this radiation, with only slight temperature fluctuations, matches predictions made by the Big Bang model, offering strong support for the theory. Moreover, the Big Bang theory accurately predicted the abundance of light elements, such as hydrogen and helium, in the universe. These elements, formed during the first few minutes after the Big Bang, are found in precisely the proportions that the theory forecasts. Alongside the evidence of cosmic expansion and the CMB, these findings have provided a robust foundation for the Big Bang model. However, the JWST's discoveries are challenging some of the Big Bang's predictions. In particular, the telescope's images suggest that galaxies much larger than previously thought could exist within just a few 100 million years of the Big Bang. This runs counter to the expectation that galaxies should form gradually through the mergers of smaller protogalaxies. In fact, the JWST's observations show fully formed, massive galaxies at redshifts greater than 10, meaning they are seen as they were less than 500 million years after the Big Bang. This level of galaxy formation appears to have happened much more quickly than the Big Bang theory anticipated, raising questions about whether the timeline of cosmic evolution needs to be revised. One of the most surprising aspects of these early galaxies is their smoothness. According to the Big Bang theory, galaxies in the early universe should be rough and irregular due to chaotic conditions of their formation. As galaxies merged and collided, their structures would have been disrupted, leading to visible signs of these cosmic events. However, the galaxies observed by the JWST appear much smoother and more organized than the theory predicts. Their structure resembles that of modern galaxies, suggesting that they formed and evolved in ways that are not yet understood. Furthermore, another critical prediction of the Big Bang theory involves how objects should appear larger as the universe expands. This is due to the so-called angular diameter distance effect, which predicts that the farther away an object is, the larger it should appear on the sky, due to the stretching of space-time. However, the JWST's images show that distant galaxies do not conform to this expectation. They are smaller than expected, challenging our understanding of how cosmic expansion events appearance of distant objects. Despite these challenges, the Big Bang theory remains one of the most thoroughly supported models in modern science. It has successfully explained a wide range of phenomena, from the expansion of the universe to the distribution of galaxies and the existence of the CMB. However, no scientific theory is ever beyond question, and the discrepancies between the JWST's observations and the Big Bang's predictions have opened the door to new hypotheses and alternative models. In light of these findings, some scientists are rethinking the origins of the universe. One possibility is that the Big Bang theory, while largely correct, may require significant modifications to account for these newly discovered anomalies. Others speculate that a completely new model might be needed, one that better explains the formation and evolution of galaxies, without relying on the singularity at the beginning of time. Some researchers are even exploring the idea of a cyclic universe, where the cosmos undergoes periods of expansion and contraction, rather than originating from a singular event like the Big Bang. Another avenue of exploration involves the role of dark matter and dark energy, which make up about 95% of the universe's total mass energy content. While we know these mysterious substances exist due to their gravitational effects on galaxies and the expansion of the universe, their exact nature remains unknown. It's possible that a deeper understanding of dark matter and dark energy could help resolve some of the contradictions between the JWST's observations and the Big Bang theory. Moreover, Alternative cosmological models, such as the steady-state theory, have gained renewed interest in the wake of the JWST's discoveries. The steady-state model suggests that the universe has no beginning or end, with new matter continuously created as the universe expands. Though largely discarded in the mid-20th century, due to the overwhelming evidence supporting the Big Bang, these recent findings may prompt a reconsideration of such ideas. Looking ahead, the future of cosmology is as uncertain as it is exciting. The James Webb Space Telescope is only beginning its mission, and in the coming years, it will continue to provide data that will either reinforce or challenge our current understanding of the universe. As more is learned about these mysterious early galaxies, scientists will have to grapple with the implications for the Big Bang theory. Will it remain the dominant explanation for the universe's origin, or will we witness the birth of a new theory that better fits the emerging data? In the end, science is not about clinging to old ideas, but about continually testing them, refining them, and sometimes even discarding them when new evidence demands it. The discovery of galaxies that defy expectations is a testament to the power of inquiry and the importance of remaining open to new possibilities. The universe, it seems, is far more complex than we had imagined, and the quest to understand it is far from over. As we peer deeper into the cosmos, we may find that the story of the universe is not as simple as a single explosive event, but a more intricate and evolving narrative that challenges our very conception of space, time, and existence itself.